Previously, we have shown how to add and subtract vectors, how to multiply a vector by some scalar quantity. Now we will just define a special product of two vectors, and that is known as the dot product. So there are two ways to multiply vectors. One of them is the dot product. So let's say that we have two vectors v and another vector w. We have these two vectors. And let's say that the components of v is v1, v2, and for w we have w1 and w2, right? So if I take the dot product of these two vectors, we can show that as v dot w. So I'm taking the dot product of v and w, and this will be just equal to v1, v2 dot w1, w2, and this will be equal to v1, w1. So we're just taking the product of my x components of these two vectors and summing it with the product of the y components. So we have v1, w1 plus v2, w2, right? And this is what I get when I take the dot product of two vectors. This is my dot product of v and w, right? And this result here, this is purely a scalar quantity, right? This is just a scalar quantity. So if I take the dot product of vectors, I will get something that is scalar. And this is also known as the inner product, right? We can also say that this is the inner product, right? Now, we will give you more details about what it actually means to take the dot product of two vectors. But now let's take a look at a few examples. Let's say that I have a vector p, and this has the components 4, minus 3. I have another vector q with the components 5 and 2, right? So if I were to take the dot product of these two vectors, so I will have 4 minus 3 dot 5 and 2, and this will be just equal to, so I'm multiplying my x components with 4 times 5 plus minus 3 times 2. So this is just 20 minus 6, which gives me 14, right? So as you can see, we get some scalar quantity, right? We just get a number here, some real number. And if I were to change the order, if I were to interchange and then take the dot product, I will have q dot p. This is 5, 2 dot 4 minus 3, and this gives me 5 times 4 plus 2 times minus 3, and this is also 20 minus 6, which is 14, right? So we can see that p dot q is equal to q dot p, right? So in the general case, if I have a vector u with the components u1, u2, and another vector v with the components v1, v2, then the dot product of these two, so u dot v, gives me u1, v1 plus u2, v2. And if I were to interchange the orders, I have v dot u, and this is v1, u1 plus v2, u2. And I can just rewrite this as u1, v1, so I'm just interchanging these two orders, plus u2, v2, right? And you can see that this and this is the same. So we can say that u dot v is just equal to v dot u, right? And from this, we can see clearly that the dot product is commutative, right? The dot product is commutative. We should know what this means. It means that if I just interchange the order, I will still get the same thing, right? So this is commutative. Now let's say that I have some scalar quantity a, right? This is some scalar quantity. Then the dot product of u with the vector v multiplied by some scalar quantity will be equal to, so I have u1, u2 dot av1, av2, and this will be just equal to u1, av1 plus u2, av2, right? And I can just factor out the scalar quantity, and I will have a u1, v1 plus u2, v2. Now, very obviously, we can tell that this is just the dot product of u and v, right? So I can write u dot av to be equal to a times the dot product u and v, right? U dot v, right? And this is for all scalars, a, u and v, right? Now let's consider once again the vectors u, v, and now an additional third vector w. So we have these three vectors. Now let's try and find the dot product. So I have u dot, the sum of v and w. So finding this, I will have u1, u2 dot v1 plus w1, v2 plus w2, right? And this will give me u1, v1 plus w1 plus u2, v2 plus w2, right? So u dot, the sum of these two vectors, will give me this quantity on the right hand side. And if I were to find u dot v plus u dot w, then this is u1, u2 dot v1, v2 plus u1, u2 again dot w1, w2. And this will also give me u1, v1 plus w1 plus u2, v2 plus w2, right? So as you can see, this and this, they're equal. So u dot, the sum of the two vectors v and w, is equal to u dot v plus u dot w, right? We have just shown this for all vectors u, v, and w. So from this, we can very clearly see that the dot product is also distributive, right? The dot product is very obviously distributive. Okay, so now let's say that we have some vector v, and let's say this has the components v1 and v2. Now, what happens if I take the dot product of this vector with itself? So if I take the dot product of v with itself, what should I get? Well, this will be just equal to v1, v2 dot v1, v2 again, and this will give me v1 squared plus v2 squared, right? Now, we have looked at how to find the magnitude of a vector, right? So considering this vector, the magnitude of this will be just the square root of the sum of the squares of these individual components, right? So we will have v1 squared plus v2 squared, right? And obviously you can see that this is just this squared, right? We can also write this as v1 squared plus v2 squared, so the square root of this whole squared, right? So this just becomes the magnitude of v squared. So if I consider any vector v, then the dot product of v with itself will just be equal to the magnitude of v squared, right? So we have just shown this. And this is for any vector v. So now that we have explained what the dot product is mathematically, we can now give you a geometric interpretation of the dot product, right? And we will be using the basic principles that we have just shown so far. So let's say that we have two vectors v and w once again, and the angle between these two vectors is given by theta, right? So this is the angle between these two vectors. So let's consider a Cartesian plane first. Let's say we have some Cartesian plane. This is my x, y-axis. This is my origin. Let's say my vector v from the origin is here. This is vector v. And we have another vector like this. And this is the vector w. Let's say that this point here, this point is denoted by uppercase v, like this. And this point here, the terminal point of w, is denoted by the uppercase w, right? So do not get these two mixed, right? Then we can very easily represent the vector v. This will be just equal to this vector v. Then the vector w, so this can be represented as w. And we can say that this length, so the length between our origin up to this point v, so this length will be given by just the magnitude of my vector v, right? The magnitude of this vector will give me this length between these 2 points. Similarly, the length from the origin to W will be given by the magnitude of my vector W, right? And if I were to then, so let me remove this. If I were to consider the distance between this point V and the point W like this, so if I were to find the distance, the length of this line segment, so WV, this will be just given by the magnitude of the vector WV. So this vector WV. Now we have shown that if we have any 2 points A and B, if we have these 2 points A and B, then the vector AB will just be equal to the vector B minus the vector A, right? We have shown this in the previous video. So we can write WV, this vector WV, as the vector V minus the vector W, and this is just, from here we can write that this is just the vector V minus W, right? So this becomes the magnitude of V minus W, right? Now how can we find this length? Well, we can just apply the law of cosines. We can try and apply the law of cosines, right? So doing so, we will have WV, so this length squared, this will be equal to OV squared, right? This length plus this length squared, so OW squared, minus 2 times OV times OW cosine of theta. So what is theta here? Theta will be the angle between these 2 vectors. This will be my theta, right? So this becomes, we have the magnitude of V minus W squared. This is equal to the magnitude of V squared plus the magnitude of W squared minus 2 times the magnitude of V times the magnitude of W cosine theta, right? And we previously showed that for any vector V, the dot product of V with itself will be equal to the magnitude of V squared, right? And as you can see, we have many of these cases, so we can just rewrite this as V minus W dot V minus W. This is equal to V dot V plus W dot W minus 2 magnitude V magnitude W cosine theta, right? And we've also shown that the dot product is distributive, right? The dot product is distributive. So this becomes V minus W dot V minus V minus W dot W, right? This minus comes from this sign here, right? And if we expand this, we will have V dot V minus W dot V minus V, so minus V dot W minus minus, so we have a plus V dot W dot W, right? And once again, we've shown that the dot product is commutative, right? If I have V dot W, this is also equal to W dot V, right? We've shown that this dot product is commutative. So this becomes V dot V minus 2 V dot W plus W dot W, right? So this on the right hand side is just equal to what we have here, right? So we can write WV squared as this here. So we will have V dot V minus 2 V dot W plus W dot W, and this will be equal to, so this is V dot V, so we have V dot V plus W dot W minus 2 magnitude of V magnitude of W cosine theta. So obviously these can cancel out, this cancels out, and we now have minus 2 on both sides, so these negative signs and 2 cancel out. So ultimately we are left with this. So we have V dot W, this is equal to this, the magnitude of V times the magnitude of W times cosine of theta. Right, so we are left with this equation here. Right, so we can say that the dot product of these two vectors will just be equal to the magnitude of v, magnitude of w, times cosine of theta, where theta will be the angle between these two vectors, right? And we can just rearrange this to find the angle. So cosine of theta will be the dot product of v and w divided by the magnitudes, divided by their magnitudes, right? So from this we can find our angle theta. Right, now once again, what is actually the dot product? When we take the dot product of two vectors, what does it actually mean? Well, this just tells us, so if I have the vector v and the vector w like this, and the angle between these two vectors is theta, then the dot product of v and w, it just tells us how much of this vector, let's say this vector, how much of this vector or what component of the magnitude of this vector is going along this direction, along the direction of w, right? So taking the dot product is very useful in many different aspects. We can also use this in physics. So when we're trying to calculate the work done on an object, let's say I have some object, let's say I have some block of 10 newtons, and a rope is attached to this block, and there is a force, there is a certain amount of force that is tugging at this object, right? And that is happening, and it's causing this object to move over some certain distance, some distance d, right? Then the work done on this object due to this force over this distance, the work done will be given by force dot the distance, right? So here we have the dot product of the force and distance, which is also equal to F times D times the cosine of theta, where theta is the angle between the force and the horizontal distance, right? So this is an example of a real world application of the dot product, right? So once again, the dot product just tells us how much this particular vector or what component of the magnitude of this vector is towards this direction, right? So let's take a look at an example. Let's say we have a pair of vectors. So we have a vector -1, √3, and we have another vector with the components 0, -2, right? So we have these two vectors, and I want to find the angle theta between these two vectors, right? So I know that the cosine of theta is equal to the dot product of two vectors v dot w divided by their magnitudes, right? So what I can do is I can find the dot product of these two vectors. I will have -1 times 0 plus √3 times -2 divided by their magnitudes, which is the square root of -1 squared plus √3 squared times 0 squared plus -2 squared, right? And this will give me -2 √3 divided by √4 times √4, which is just -2 √3 divided by 4. And this is just -√3 by 2. So I found that cosine of theta is equal to this, -√3 by 2. So for what angle of theta do I get -√3 by 2? Right, cosine is negative in the second and third quadrant. So we can find that theta will actually be equal to 150 degrees, right? Theta will be 150 degrees. So the angle between the two vectors that we were given here will be 150 degrees, right? Now you can try an example for yourself. Let's say we have a vector 2, 1 and another vector -2 minus √3 -1 plus 2 √3, right? So let's say this is the vector v, this is the vector w, right, with these components. So what is the angle between these two vectors, right? What is the angle between these two vectors? So if you try this for yourself, you will find that theta is equal to 120 degrees. This should be your answer, right? Now let's say that we have two vectors v and w. Once again, we have these two vectors. Now, we can say that these two vectors, so v and w, these two vectors are orthogonal. We can say that these two vectors are orthogonal if the dot product, if their dot product is equal to 0. So the dot product of v and w is equal to 0, right? So these two vectors are orthogonal if their dot product is equal to 0, right? So let's draw these vectors. Let's say that from this point, let's say this is our origin, we have a vector in this direction, this is v, and we have another vector in this direction, let's say this is w, and the angle, once again, between these two vectors is theta, right? So here we're considering two non-zero vectors, right? We're considering these vectors to be non-zero, and they're starting from this same point, right? And we know that the dot product of these two vectors will be equal to this expression, right? So from this, when can we have our dot product to be equal to 0? We know that the magnitudes of these two vectors, they cannot be 0, right? Since we're considering them to be non-zero vectors. So that means the only case for which the dot product is equal to 0 will be when cosine of theta is equal to 0. So when is cosine of theta equals to 0? Well, cosine of theta is equal to 0 when theta is equal to 90 degrees, or when it's pi by 2 radians, right? So when theta is 90 degrees, the dot product is equal to 0. Meaning, if our vectors are completely perpendicular to each other, so if the angle between these two vectors is 90 degrees, then these two vectors are said to be orthogonal. The dot product will be equal to 0, right? So the vectors v and w, they are perpendicular. They are perpendicular if and only if the vectors are orthogonal, right? These two vectors will be perpendicular if and only if they are orthogonal, right? So if two vectors are orthogonal, it means they're perpendicular. The angle between them will be 90 degrees. And we can denote that two vectors are orthogonal like this. We have the vector v, we have this symbol, and the vector w. This means that these two vectors are perpendicular. And since perpendicular vectors are orthogonal, we can also say that these two vectors are orthogonal. And we can denote it like this. Right? And our zero vector, the vector 0, this is actually orthogonal. So if I have a zero vector, this will be orthogonal to all vectors, right? The dot product of any vector v with the zero vector will always be equal to 0, right? So the vector 0 will be orthogonal to any vector, every vector.